So, hi, everybody. Welcome to the 7th Extreme Universe Colloquium. Today, we are very happy to have Professor Sandip Trivedi, a world-famous string theorist from Tata Institute of Fundamental Research, which we call the TIFR in Mumbai, India. Okay. Before we start, let me introduce Professor Sandip Trivedi. Professor Trivedi completed his Master of Science in Physics from IIT Kanpur, 85. Then he went to the US Caltech and obtained his PhD in 90, where he worked with Professor Prescott. He also worked with Professor Feynman while he was at Caltech. And later he went to the Institute for Advanced Study, Princeton, as a postdoc. And then he went to the Caltech as a second postdoc. Then from 94, he joined Fermilab in the US as a faculty member before he came back to the India in Tata Institute in 1999. Professor Trivedi contributed significantly in string theory. His most famous work, which he has done with Professor Kachiru, Karosh, Linde in 2003, is so-called the KKLT construction of Dojita space and accelerating universe realization in string theory. Before that, Dojita vacuum in string theory was thought to be somehow impossible due to several novel theorems. But in that paper, he showed that, in fact, Dojita is possible in string theory. Sandip's work gives a significant impact on the string theory community and then open up the idea of the string theory landscape. His paper is, KKLT paper is cited more than 3,000 according to the Inspire Now, and which actively people are studying. Professor Trivedi also contributed other branch of physics as well, including black hole information paradox, radius shift dictionary, non-supersymmetric attractor, condensed matter, extended Hilbert space definition, and many. He has also awarded several prestigious prizes, including Shanti Swaraj Bhatnagar Prize, Infosys Prize, the World Academy of Science Prize, and HK Philodia Awards, and so on. So let's invite Professor Trivedi. Sandip, so please start.
Okay, thank you very much, Nori. That's a too kind an introduction. I certainly don't deserve it, but thank you anyway. And thank you very much for this great honor of giving a colloquium in your forum. So the title is Entanglement in Gauge Theories, Matrices, which will also be gauge systems, and the connection possibly with space-time entanglement. Here we go. Not changing slides. We tried it and it. Oh, yeah. Sorry, 1 minute. Okay. So I'll begin with an introduction to the idea of entanglement. Now, I know many of you are, of course, real experts, some of the leading experts in the world. But since it's a colloquium, I hope it's okay if we start by first reviewing the key ideas. And then I will go to gauge theories, where it's a little subtle to define precisely what entanglement means. And we will give a definition and understand operationally what it means. After that, we'll go to these matrix theories and discuss entanglement in matrix theories. And these matrix theories are of interest from the point of view of ADS-CFT and providing an understanding of how space-time emerges. And therefore, we will try to relate the definition in matrix theory to one in space-time. That is a proposal. The second part here in the point 3 remains to be seen, but we'll at least discuss it. And then I'll end with some conclusions. And, please feel free to ask me questions along the way. And also afterwards, Nori was telling me that we'll have, it's possible to have a somewhat extended question-answer session, which I'm happy to be there for. So please also feel free to ask me then. So let's get going. We are in the midst, as many of you know, of exploring a new frontier of science today. It does not pertain directly to the very small, say deep inside the atom, or the very large, way beyond our galaxy, or even the very many, involving very many atoms, molecules, or neurons. It's a different kind of frontier. And this frontier pertains to our growing understanding of quantum mechanics, its true meaning and significance. Now, at first this might seem strange because quantum mechanics is over 100 years old. one would think one has understood it completely. But the quantum world is so different from the classical one where our intuition and day-to-day experiences are based that it is taking a long time to understand its true strangeness. And doing so is leading us to this new frontier of science. Also, since quantum mechanics, after all, provides the bedrock of our understanding of so much of science, this new frontier now promises, in a very exciting way, to have implications for many branches of science: physics, chemistry, computer science, some other aspects of engineering, and even mathematics. And that's why we are all, some of us, so excited about it. Much of this strangeness of quantum mechanics has to do with a property called entanglement, which has no classical analog. And that's what this whole colloquium will be about. Since entanglement is playing such a key role in these recent developments, the new frontier is often referred to now as the entanglement frontier, which is a phrase coined by, as Nori was mentioning, my thesis advisor, John Preskill. So I have John's picture here. And that's the kind of frontier then people are looking at. Now, of course, we all know that the underlying description of quantum mechanics is very different from classical mechanics. It's in terms of a wave function, which should be thought of as a probability amplitude, and the contributions to the wave function from different paths can interfere, and finally give rise to a probability which is the mod square of psi. But there's so this is itself very strange. We learn about it as an undergraduate and then try to make our peace with it. But there's something else which is also strange. And this something else is the property of entanglement. It was Einstein who actually first put his finger on this additional weirdness in quantum mechanics, and it caused him a lot of disquiet. It's sometimes called a kind of spooky action at a distance. And it refers to the fact that the wave function in quantum mechanics is intrinsically non-local. Even though all its consequences are local, all disturbances propagate locally, at most at the speed of light, even so, the intrinsic description is non-local. And it's this kind of non-locality which we have in mind when we talk about entanglement. So let's try to understand that a little better. These kind of non-local correlations don't have a classical analog, as I was mentioning. And a quantitative measure then of this kind of non-local correlation is provided by entanglement entropy. And that's the quantity we'll spend quite a lot of time trying to define in various contexts today. Now, just to give you an example, and I apologize, I know it's elementary for many of you. Just to emphasize the non-locality, I've taken two electrons here, say in a spin 0 state. One of the electrons, say the first one is on Earth, the second is in Andromeda, let's say, just to dramatize the non-locality. This state of the two electrons is an entangled state. If the first electron is up, the second is down. If the first is down, the second is up, so they are correlated. And it's a very interesting kind of correlation because, as you know, if you just measure the spin of the first electron along any axis, actually it can be it will with equal probability be up or down. So it's completely uncertain. Yet, despite this uncertainty, there is complete certainty that once you measure, say, the spin of the electron on Earth, the spin in Andromeda is totally fixed. If the first electron turns out to be plus along any axis, the second in Andromeda will have to be minus. And similarly, if the electron on Earth is of minus magnitude and sign. Okay, so this kind of entanglement then, a correlation is what we mean by entanglement. Einstein was very worried about it. He felt if physics is local, then there should be an intrinsically local description also of a system. Why does there have to be this kind of non-locality? And he suggested that perhaps it was because we didn't have a complete description as yet in quantum mechanics, that there was a more fundamental underlying description which was local and in fact classical, with additional hidden variables. If you don't have those variables in your description, then maybe you get the kind of probabilistic description of quantum mechanics and you get this non-locality. But if you kept the hidden variables in addition, you would have a local description. And it took many, many years. You know, the EPR, famous Einstein-Podolsky-Rosen paper, is written in 1935, I believe, and it took 30 years for John Bell in his brilliant work to realize that actually, you know, entanglement is a very interesting way to distinguish quantum systems from classical ones with local hidden variables. You could actually experimentally tell apart the effects of these quantum correlations due to entanglement from how a classical system with additional local hidden variables would behave. And you know, this, look at it takes 30 years. The mathematics we all know is utterly trivial. Anyone can do it in high school, actually. But it takes 30 years because quantum mechanics is so strange. And of course, as you all know, the differences between these classical systems and quantum ones are summarized by Bell's inequalities, and experiments, for example, done by Alain Aspect and his group, have brilliantly confirmed that quantum mechanics is actually correct and ruled out these local hidden variable theories, which Einstein suggested might be the underlying description. So quantum mechanics, quantum systems describe nature, and they have intrinsically these kind of non-local correlations, which give rise to Bell inequality violations. Okay, now let's try to understand how to quantify this kind of correlation. The electrons in the state I was mentioning, up, down, minus, down, up, are entangled and correlated. But of course, take the electrons to both be, say, spin up. That's also a correlation between the two electrons. What's different between them? Can we make it precise? Well, one physical difference is that the electrons in the state above will lead to Bell's inequalities if you do the correct kind of experiment, but the electrons in the state below will never lead to these violations. So that's one difference, but how can we make it mathematically precise, measure this kind of correlation? And the answer is, one very good measure is provided by entanglement entropy, and this is defined as follows. You first define a density matrix for the first electron by tracing over the second electron here. And after that, once you have that density matrix, which acts only then on the first electron states, you compute its what's called von Neumann entropy minus trace rho log rho, and that gives us a measure of the entanglement, and it is called the entanglement entropy. For this state, the entanglement entropy turns out to be log 2, and that's essentially because the first electron can be, once you have lost any information about the second one and you compute the density matrix, that first electron has equal probability of being in the state up or down. So this density matrix corresponds to a diagonal matrix 2 by 2 which is proportional to the identity, with equal probability of being in the two states, and therefore the measure of then the entropy is log 2 because they're two equally probable states. Okay, more generally, if you have the density matrix and its eigenvalues are pi, you sum over all the probabilities pi, you get 1, then the entanglement entropy is defined as minus the sum over all the states pi log pi. Okay, and this entropy is therefore the von Neumann entropy of the density matrix. So that's how we can define the entanglement entropy. If you took this state with both spins up, which didn't have any violations of Bell's inequalities, then the entanglement entropy would turn out to be 0. So that tells us that the entanglement entropy is a good measure also of this weirdness that allows quantum systems to behave differently from classical ones. Okay, so now that completes my introduction, and let's go now to studying entanglement entropy in gauge theories. Now, as you all know, gauge theories are very fundamental to our description of nature. 3 of the 4 fundamental forces of nature, the strong interaction and the electroweak interactions are described by a gauge system, a gauge theory, SU3 cross SU2 cross U1. And the fourth fundamental force, gravity, is also a kind of gauge theory, although the discussion of entanglement in gravity is much more complicated. So in this part of the talk, I'll be discussing only gauge theories of the type which are there in the strong and electroweak forces and their analogues, discrete gauge theories and so on, which can also occur in nature. So gauge theories are quite ubiquitous. They also often emerge at low energies in condensed matter systems. As many of you know, this is a very beautiful set of developments. Often you don't have any gauge redundancy in the underlying theory, but it emerges at low energies, and therefore there are additional gauge symmetries that sometimes you have to deal with in condensed matter systems. And given the ubiquitous nature of gauge theories, it's of course quite important to understand precisely how to define entanglement entropy in such systems. And let's then turn to that task. This turns out to be subtle, and let me first try to explain the reason as to why it's subtle. You know, in a spin system, say like the two electrons we were talking about, the degrees of freedom are local. Each spin was described, each electron, whether on Earth or on Andromeda, were described by a local spin degree of freedom. Of course, these spins were correlated, but they were local degrees of freedom. This fact that there are local degrees of freedom is the underlying reason why it's then conceptually straightforward to define an entanglement entropy for spin systems. In contrast, for a gauge theory, as we'll see, the gauge invariant, the physical degrees of freedom are intrinsically non-local. For example, these physical degrees could be described by electric and magnetic fluxes or lines of force. And these have to satisfy certain continuity conditions. For example, because they must meet the Gauss law constraint. That means if you're looking at some region of interest, the electric and magnetic lines of force can't just abruptly end at the boundary of that region. They have to continue forward from there. And this correlates the fluxes in the region of interest with those outside the region of interest. And that makes then the gauge invariant of physical degrees of freedom intrinsically non-local. Now, because you can't vary these degrees of freedom inside the region and outside independent of each other, unlike the spins. Okay, and it's this non-locality in the intrinsic degrees which then makes it difficult to come up with a good measure of the non-local correlations in the system, because the degrees of freedom themselves are not local. Okay, so let's try to understand that a little bit better, and then we'll try to give a definition of entanglement anyway in gauge theories and discuss it. So here is, let's take electromagnetism without charges. No electric, no magnetic charges, then you know that these are two of Maxwell's equations, divergence of E equals 0, Gauss's law, and also divergence of B equal to 0. And these, as I was saying, then require the lines of force or the fluxes to be continuous. For example, I added two charges here just to make it more physical, but it would also be true in electromagnetism without charges. If on the boundary shown in red there are no charges at all, then these lines of force which are going from the plus to minus charge, they can't abruptly end. They have to continue past the boundary, and that means you can't vary them on the left and right in an independent manner. Okay. In the quantum theory, by the way, for example, if we quantize the system in A0 equal to 0 gauge, then Gauss's law is a constraint which needs to be imposed on the physical states, or on the states, to make them physical, to make them gauge invariant. And so that's how in the quantum theory these continuity equations emerge or arise and need to be imposed in the system. Okay, now just very briefly, not to dwell too much, the difference again in the spin system is, as I said, even though the two spins may be correlated, in principle, the first electron could have had a spin which is completely different from the second one with, very different or no correlations. For example, this state, as we were saying, where they're both plus is also allowed, or the first one could be, in this case, in a pure state, which is a linear superposition of up and down, and the second one could be just in the up state. So the two electrons can have completely independent spins. Mathematically, this means that the Hilbert space of the two electrons of the full spin system admits a tensor product decomposition. In this case, can be written as the tensor product of the two electron Hilbert spaces. Okay, the first one refers to the spin of the first electron, the second one to the spin of the second electron. Because of this tensor product decomposition, it is then straightforward to define the entanglement entropy for the spin system. As you saw, we can trace over the degrees of freedom in the second Hilbert space, say, over H2, define a density matrix acting on H1, and with that density matrix then compute the entanglement entropy. Now, in contrast, since the electric and magnetic fluxes cannot be varied independently, you don't have a Hilbert space of the full system which admits such a tensor product decomposition. And because of that, it is more difficult to try and define the entropy. This is the essential complication we have to deal with. Okay, and that's what we tried to deal with some time ago. These are three of my students who made important contributions in a series of papers. There are also many other very, very important works, in particular this paper of Cassini, Huerta, and Rosabel, which really was very, very insightful and got us thinking about it. Many papers by Donnelly, many more other papers by Cassini and Huerta and so on, and many other people who have contributed in important ways. I'm sorry, I'm not listing them all here, to this understanding of entanglement in gauge theories. Okay, let me go ahead. So the approach we took was to actually embed the physical states which meet these constraints, Gauss law constraint, in an extended Hilbert space which allows for states which don't meet this constraint. Of course, these additional states are not gauge invariant, but one can consider anyway such an extended Hilbert space. And in a simple enough way to quantize that additional Hilbert space, the full extended Hilbert space still has a nice positive norm and so on. And one can then, what one then finds is that this extended Hilbert space now does have a tensor product structure, because you have allowed the fluxes inside and outside to vary independent of each other without meeting the Gauss law constraint. Okay, and so once you do that, once you embed in the extended Hilbert space, then in a very straightforward way, you can do basically what we were doing for the spin system, and define an entanglement entropy. You again get a Hilbert space which is a tensor product, say, of the inside H1 times the outside H2, and then trace over the outside and obtain an entanglement entropy. This result, importantly, even though we extended the Hilbert space, the final result, because we are starting with a physical gauge invariant state, one can show is gauge invariant. No lack of gauge invariance is present in the final answer, which is therefore a physical result. It does not depend on any choice of gauge or anything. It works for gauge theories in general, including abelian and non-abelian ones, with and without matter. And importantly for the experts, this definition agrees with a path integral definition one can provide for entanglement entropy based on the replica trick. That path integral definition is manifestly gauge invariant, because you can prove that the path integral for gauge theories, even over the kind of manifold one has to carry out the path integral to compute entanglement entropy, is gauge invariant. So the path integral was anyway giving us a gauge invariant definition, but it was unclear in terms of states what that definition meant, and this extended Hilbert space definition, one can show, agrees with that replica trick definition. So that's another nice property The non-trivial thing, actually, I should be more precise when I said there's a Hilbert space structure, is the following, that actually more correctly, the Hilbert space of the full system is not a tensor product, but it's a sum over sectors, each of which is a tensor product. Each sector is labeled by the flux, which makes its way from one side to the other, and then the full Hilbert space is a tensor product in each sector, and then a sum over all sectors. So this is the structure, and really the fact that the fluxes have to meet this continuity condition results, when you think in terms of the algebra of operators, gauge invariant operators pertaining to, say, the region of interest, whose entropy we want to calculate, it results in that algebra having a non-trivial center, as I mentioned here. And this fact was really brought to the fore by Cassini, Huerta, and Rosabel, who had discussed the abelian case. But in fact, that structure is true also more generally, and it's true in the non-abelian cases as well. And you have to define the various elements of the center as well as then the sectors carefully in the non-abelian case in an appropriately gauge invariant manner. But that can be done, and then the entire structure also generalizes. So this is a more algebraic way, a way through operators to understand how the gauge theories work and how they're different from spin systems. Now, just to tell you, you can give a definition, and that's all very well, but operationally, we of course want to know what this definition really means. And here are two slides which I hope can bring that out a little bit. One way to think about the entanglement entropy, the entanglement entropy, say for a spin system that we were talking about, is through the following kind of operation, or if you wish, protocol, which is called entanglement distillation. There's a similar thing called dilution, which uses teleportation, but I won't go into that here. But let's talk about distillation. So the idea is the following. Suppose we have two systems, A and B. They have some amount of entanglement between them. Say this could have been the first electron we started with, and the second one, B could be the second one on Andromeda, A could be on Earth. They have some entanglement. We want to measure how much it is, or instead it could be many spins in system A, many other spins in system B. How do we try to make that operationally meaningful? What is the entanglement between them? And the answer is this: we use Bell pairs. That state of two electrons, I talked about the one which has spin 0, that's called a Bell pair in honor of John Bell. And so what we would try to do is to say the following: our currency for entanglement is the number of Bell pairs. How many Bell pairs worth of entanglement does this system AB possess? If we can make that precise, then that is the entanglement in log 2 units we would like to associate with the system A and B. Each Bell pair, if you remember, had entanglement log 2. So if you can extract n independent Bell pairs from this system, then the entanglement we'll associate with it is n log 2. So how many Bell pairs can there be? So what we do is we start with some number. We don't quite know how much entanglement we'll be able to extract, but we start with some number. Let's call it n to begin with. 2n of these qubits or electrons. Each spin half system is called a qubit, as you know. So we start with them. Initially, they are completely unentangled. They are shown in blue dots here. And they have no entanglement. All the entanglement resides between A and B. Then what we allow ourselves to do are unitary transformations on A and on the first set of these qubits shown in the left. That's a way of saying we allow the most physical operation to happen between them when we couple the two systems, because these operations will take the form of unitary transformations. For example, if there is a coupling between the Hamiltonian of A and the first set of qubits on the left, then over time that coupling will generate some kind of a unitary transformation between the Hilbert space of A and the left side of electrons. So we allow ourselves the most general such unitary transformation. We also allow ourselves the most general unitary transformation acting on B and the right-hand set of electrons. Now the important thing is we don't allow unitary transformations that allow B to couple with the left set of electrons, A to couple with the right set of electrons. So the unitaries in a sense are local. The A unitaries can couple to the left electrons, the B unitaries can couple to the right electrons. Okay? But then we allow the most general such unitaries. And after that we ask, at the end of the day, what's the maximum number of Bell pairs among these qubits or electrons? I keep going between them, sorry. What's the maximum number of Bell pairs among the qubits here, which were initially completely unentangled? How many maximum number of such Bell pairs can we produce through such local unitaries? Okay, and we try to extract as much as we can, and the number of Bell pairs we end up producing, that's our operational measure of entanglement in the system. Now it turns out if you had a spin system, you can show, by the way, the experts will know, I'm simplifying the discussion to make it absolutely precise. You have to define this protocol in an asymptotic sense by taking many copies and so on and so forth. Those are details, but the key physics point is what I'm mentioning here. So there are a few caveats here, but it's all well known. You can read about it in any standard textbook. This is the basic idea. Okay, now for a spin system, if you had, say, a spin system A and B with some entanglement, it turns out you can show you can extract all the entanglement in this way, transfer it to these unentangled qubits, and the amount of entanglement you will. Sorry, I think there's some. Hi, can you hear me?
Yes, I muted.
Okay.
Somebody entered without muting. So,
Okay. So so for a spin system, the amount of entanglement you can extract in this way, number of Bell pairs among the qubits you can generate, exactly agrees with that entanglement entropy we had defined, the von Neumann entropy coming from the density matrix. Okay, so that is a known property for the spin systems in general, for any system which has a tensor product, just a single H1 tensor product H2 structure, HA tensor product HB structure. But as we were discussing, gauge theories are different. They have these additional constraints we have to deal with, and operationally what turns out to be the case is that means that you cannot distill all the entanglement into Bell pairs. So the entanglement you compute, say by constructing the Hilbert space in the extended, say by constructing the density matrix in the extended Hilbert space I was mentioning, then computing its von Neumann entropy, that entropy does not correspond fully to the number of Bell pairs you can extract and the amount of violation of Bell's inequalities you can get from the system. And this is the key difference, if you wish, between then gauge systems and spin systems. How much can you extract? How much is left unextracted? A kind of classical piece which you can't extract into Bell pairs. That also one can make quite precise. I don't write down the formulas here, but you can write it down in a fairly precise way. And of course, computing it always is not very easy, but in principle, both parts can be independently computable. Of course, sometimes you have to deal with ultraviolet divergences and so on, but in principle are computable, say with UV cutoffs. Okay, so so the key difference then is that for gauge theories, the entanglement is the entropy is not all distillable into Bell pairs. There is a non-distillable amount. Now the distillable amount, of course, tells you, as I was saying, how many Bell pairs you can extract, but it turns out the non-distillable amount is also quite interesting. For example, in some topological systems like the toric code and Chern-Simons theories, in fact, the full answer you get for the entanglement entropy. These are gauge systems, as many of you know. The toric code has a Z2 gauge symmetry. Chern-Simons systems are, of course, gauge theories also. So you can apply these definitions to them. And it turns out that the non-distillable amount in many of these topological systems is in fact the full result. There is a very famous topological entanglement entropy, which one associates with these topological systems. It's constructed out of the entanglement entropy I was mentioning by taking various combinations. And all of that actually corresponds to the non-distillable entropy. So the non-distillable part also is actually quite interesting, and in fact it can often be a good measure of the topological nature of the state, can serve as an order parameter, which helps us to classify the different kind of phases of matter. So both parts are interesting, both parts can be defined and made precise, and that's the story then with entanglement entropy for gauge theories. I hope I'm at least making some sense. It's on these Zoom talks, it's hard to tell. If there's any question you want to ask now, I'm happy to try and give some clarifications, Nori, as you like, or I can go on, whatever you feel.
We will take the time for the question later. So everything is clear, so you can just go ahead.
Okay. Is my pointer something you can see, if
Yes.
I may ask? Okay. Okay, so let's go on then to the third part of the talk, which deals with matrix theories and entanglement in these matrix theories. I'm sorry this will be perhaps a little more technical for the wider audience, but I'll at least try to explain to you what is the question we were trying to address. And I think that part should be clear enough. And some of my slides are a little busy, as you can see, but many of the details are not really important, and I will try to bring out what are the crucial important points as we go along. So the kind of matrix theory we would like to deal with is shown here in the action. The first thing to say is this is the action. It's only integrated over time. So these are really quantum mechanics systems. And the main difference is that xi, these objects, are n by n matrices. In this case, of great interest in string theory, there are 9 of them, 9 matrices. These correspond to the 9 spatial directions which are present in string theory. So total 10, time, and 9 directions. Those 9 directions here have become matrices. And there are 2 terms here. One, the first term is a kinetic energy term. It's got x dot square in it. The second term is a potential energy term. It's got some commutator of matrices and then the square of that. The kinetic energy term, you'll see, has a covariant derivative. There is a gauge field here, AT, and that shows you that actually what we are dealing with is a gauge system. Of course, it's just quantum mechanics, but there's a gauge symmetry here, which I'll come to in the next slide. And that is sort of the connection with the earlier part of my talk, that in a sense, our general thinking of gauge theories then is something we can hope to use to also try and ask about entanglement in this kind of system. Okay, now there are various other parameters here. There's a scale LS. That scale is put in for dimensional considerations. It corresponds to the string scale. Here we have another factor of LS, again put in from dimensional considerations. N is the size of these matrices, n by n. So these matrices have n squared degrees of freedom. If you often colloquially, I'll also start doing this, I refer to these degrees of freedom as color. This is of course not QCD, but since it's a gauge theory, so these are color, systems with color degrees of freedom. And there's another parameter GS, which corresponds to the string coupling. That won't be very important. I won't go into details. None of these parameters will be too important. Main thing is it's a matrix theory, It's a gauge system. It's got color degrees of freedom, these n squared degrees of freedom. And what we are trying to do, what we will like to do is define some measure of entanglement in these color degrees of freedom of the matrices. Okay, that's the main question, which I'll try to make clearer as we go along. Okay, so it's a UN gauge theory. The xi's are n by n matrices. They transform under the UN gauge transformation as xi goes to u. U can be a function of time, I should have said. Xi u inverse. And therefore the xi's behave like adjoint degrees of freedom. At is a gauge field, so it transforms in a way appropriate for a gauge field under this gauge transformation. It also belongs to the adjoint. It's an adjoint gauge field or whatever, as usual. And the action I wrote down because it involves the color degrees of freedom. Because it involves the covariant derivatives, you can easily check, and it has a trace both here and here is gauge invariant. Okay, so that's our system. Now, as I said, what we want to ask is how entangled are some of the degrees of freedom of the matrices with the other degrees of freedom. And again, the fact that it's a gauge system, you'll see, makes this a somewhat subtle question. Okay, so naively, what we might want to say is, okay, you have an n by n matrix, take the first m by m block and ask how entangled is it compared to the others. The trouble is, so this is the kind of question you might start off with. The trouble is, a gauge transformation, a UN gauge transformation will mix up this block, blue block, with everything else. So there's no gauge invariant sense to begin with in asking that question of how entangled is this m by m block with the rest. So how do we make precise some gauge invariant version of this question? Okay, this is the issue. And this was addressed in several papers. In particular, I'll talk about the work I did with Shumit Das, Anurag Kashyap, Gautam Mandal, and also Xijong Liu in these two papers. There's also a very nice paper by Mazenk and Renard and by Hampura et al., which also make very important contributions. Okay, now before I tell you the kind of definition we'll explore, you might ask, what's the context? Why are you interested in these kind of matrix models? So I'd like to tell you a little bit about that for the non-experts again. And partly I want to do that because it'll provide the context for our definition, which will actually be motivated by some of the considerations or the background I'll now describe to you. So why are these kind of matrix models interesting? Well, you have all, of course, heard about the ADS-CFT correspondence, which is one of the great developments of the past 2 decades, really thanks to the brilliant work of Juan Maldacena. And what this correspondence and related developments have shown us is that these kind of matrix theory I was discussing and their higher dimensional analogs. So this matrix theory I was discussing was just in time, it was just quantum mechanics, but you can consider similar gauge theories in several spatial dimensions, so in 3+1 dimensions or 2+1 dimensions, even higher dimensions. So those kind of gauge systems then often tell us about how gravity can emerge or arise in smooth spacetimes in appropriate limits, and if that field theory system is a conformal field theory, then on general grounds we can argue that the gravity description must be anti de Sitter space. So that's the kind of insight which has come out of these past 2 decades of work, and that's the kind of context we have in mind when we study these kind of matrix models, that they can actually teach us something deep about space-time, how it emerges, and they kind of provide an underlying non-perturbative definition, in fact, for quantum gravity in at least these kinds of spacetimes, anti-de Sitter space, or kind of related spacetimes which arise for other matrix systems, including the matrix theory I was discussing. So let me tell you just a little bit more about all this, and then we'll go back to the matrix theory. Perhaps the best known example of ADS-CFT, as many of you know, is when the field theory is in 3+1 dimensions. It's called the n = 4 super Yang-Mills theory. In this case, you have ADS5, actually, and this will be important for our talk, you have ADS5 cross a additional space, a 5 sphere in this case, because string theory, of course, lives in 10 dimensions. And so altogether 5 plus 5 makes 10. That's the string theory gravity background, which is described by this field theory, conformal field theory in this case. The 3 dimensions along which the field theory lives is part of, also shared by the 5-dimensional anti-de Sitter space. 3 plus 1, I should say, the 4 dimensions including time are shared here. And some of the additional directions are not present in the field theory directly, but they are encoded in the degrees of freedom of the field theory. Okay, now in the matrix theory we are talking about, as I was discussing, the matrix theory has only time. The bulk system will still arise, or the gravity system will still be a solution in string theory, so it will have time and 9 spatial directions. Those 9 spatial directions are not ones in which the quantum mechanics lives, but as you saw, the quantum mechanics has matrices, 9 matrices. Those matrices are going to encode the information about the 9 spatial directions of the gravity theory. Okay, so the boundary theory only lives in time, and the spatial directions are encoded in these degrees of freedom. And the question, when we are trying to ask how entangled are some of the matrix degrees with the rest, we are therefore actually trying in a sense to ask about entanglement in space-time, but asking it in the matrix description. Okay, that's the idea. Okay, well, here's a picture. Everyone's seen this, but in ADS CFT, you have the boundary theory in which the CFT lives and the bulk in which gravity lives. Just one more small thing and then we go on. The D branes, the way this correspondence arose, as you all know, is you have these objects called D branes in string theory, and if you study their excitations, those excitations have 2 kinds of descriptions. You can either describe them as a gauge system, a gauge theory without any gravity, or as excitations in a gravity theory where the gravity background arises by solving for these D branes in the gravity description. The equivalence between these two gives rise to this correspondence. Okay, here is the background in more detail, corresponding the gravitational background corresponding to the kind of matrix system I was discussing. It arises from D branes by taking their low energy excitations. And okay, it looks very complicated. The only important thing is there's time, there are 9 directions, there's some function of the radial coordinate. All the details are unimportant, but just to say there is a kind of gravity background. In an appropriate region of space-time, it's smooth and under control, and we can hope to try and understand that region from the gravity perspective and ask what we can learn in matrix theory about it. One last thing about these systems, then let's go back to the question we asked. The gravity side actually also has a situation. This solution actually is one where all these zero branes, D0 branes came together, but you can also separate them, and you have interesting solutions where they are where they are not far necessarily, but separated from each other. This is called the Coulomb branch. Each of these branes will have a location in 9 dimensions, so it will be specified by 9 coordinates. If you have n branes, you will have n of these branes, each of them with these 9 coordinates specifying them. And there's a one-to-one correspondence, nice correspondence between these whole class of solutions on the gravity side and similarly an entire class of solutions, a moduli space of solutions on the matrix model side. The fact that you have this kind of correspondence gives us confidence that actually the 2 systems are 2 different descriptions of the same thing. Okay, now we are ready to get going with our definition. And the definition I'm going to try and give you is actually motivated then from this bulk picture. So you saw that the bulk had 9 directions, spatial directions, and we may want to ask a question like, how entangled are the degrees of freedom, say, when we look at the region where x1, one of the directions, is greater than some value. So that divides space into 2 parts. How entangled are the degrees of freedom in this region with the rest? What kind of entropy can we give to it? Now in the bulk, it's hard to make this question very precise. What we'll do is take this as a motivation, try to translate it to a matrix theory question where we will be able to give a precise definition. So as you saw, this direction became a matrix. What we'd like to ask is, take the region, we'll make this precise, take x1 greater than some value, same value a, can we ascribe an entanglement in the system to this kind of constraint? Okay, can we do it? And the idea is the following. I'll describe it in a particular gauge, but again, it will turn out that the final answer is completely gauge invariant, which one can show. So let's do the following. To implement this constraint, let's go to the gauge where x1, this one matrix, is diagonal. Now, each of these matrices transform under a UN gauge transformation, and you can always make one matrix diagonal. So we make the first one here diagonal, and then we arrange the eigenvalues, say, in descending order here. So the first few are bigger than the rest and so on. And we ask how many of these eigenvalues meet the constraint of interest, that they are bigger than this value a. Now let's say for this particular matrix, the number of such eigenvalues was m. Then that tells us, in this gauge at least, which m by m block to focus on for computing the entropy. Okay, so we've gauge fixed, keeping in mind the constraint. We've decided then, looking at x1, what the m by m block is, and then for all the 9 matrices, the other matrices won't be diagonal in this particular gauge, but never mind, we can take the m by m blocks for all of them, trace over the remaining degrees of freedom, construct a density matrix, and compute its entropy. This is the basic definition one can give. In the Hilbert space does admit a tensor product decomposition for each sector corresponding to any value of m, and then you can compute the density matrix, and by tracing over all the remaining red blocks, and that gives you an entropy. This is at least one version. I'll come to another version shortly. Then in general, you can have many sectors, because only the number of eigenvalues of x1 which met the constraint can be 0, 1, 2, all the way up to n. For each sector, you have to compute this entropy and sum over it, and that gives you the full entropy, the entropy associated with these degrees of freedom, along which the matrix theory does not live, because it only lives in time, but which correspond to these matrices which are present. And because the gauge theory doesn't live in these directions, because the matrix theory is only along time, we call this target space entanglement. I'll come back to that. Okay, so that's the definition. You can show it's gauge invariant. You can show that it's gauge invariant, although we used a particular gauge, and actually even provide a fully gauge invariant definition in terms of a subalgebra, etc., etc. If you like the algebraic way of thinking better. So all that can be done, but the physics is just what I described to you in terms of these simple matrices. Now actually there are two versions. You may say, if I have a m by m block, if I have these m eigenvalues, I will only keep the m by m block, or you may want to keep the off-diagonal 2 blocks of size n minus m times m, or m times n minus m, b and c also, and trace out over the red block, which is just n minus m times n minus m. I'll show that to you in terms of pictures. So there are actually two versions of the definition. Both are gauge invariant. Both provide a kind of definition for this notion of entanglement associated with these matrices. I'll quickly show you a picture, and then we'll stop. Now, but just to say this, I started with the constraint x1 greater than 0, but it really can be any constraint involving the matrices, because any combination of the xi's is a n by n matrix. For example, if you had squares, that's also, and you sum, that's still a n by n matrix. You can diagonalize it, so you can repeat this for a general constraint and so on, and construct a entropy along the same lines. I'll tell you physically in terms of the bulk what we are doing. Roughly, if you had a configuration where these zero branes were separated from each other. The value of the zero branes along the x1 direction is the eigenvalues of the x1 matrix. And what we are saying is keep the branes, say in this case 4 of them, which meet the constraint x1 greater than 0 if the value of that parameter a was equal to 0. So you want to keep all degrees of freedom meeting the constraint x1 greater than 0. In this case, there'll be these 4 eigenvalues or 4 branes. And then you have the choice. In one version, you keep the degrees of freedom associated with strings running between the branes all to the right. And that was the first version. In the second version, you allow for the strings which cut across, but as long as one end of them at least ends in the region of interest, you keep those degrees of freedom. You don't keep strings which just begin and end in the other region of freedom. So anyway, there are these 2 versions, but both are gauge invariant, and both are a kind of measure of the entanglement in color space, which roughly is analogous to asking a question in the bulk about entanglement. Let me try to just say a little bit more about that. It's tempting, we make this speculation, but it remains to be seen that in fact the answer we compute in the matrix theory might agree precisely with a bulk entanglement. What kind of bulk entanglement? Well, there's only one natural entanglement one can think about in the bulk, which is area in G Newton units. So the idea was you take the same region in the bulk, say x1 greater than a, and you compute its area, and area over 4 G Newton in the bulk is what we are computing in the matrix theory. Of course, in the bulk, this is not a gauge for the experts. As you know, this is not a gauge invariant way to specify the region of interest. But what the matrix theory is trying to do is make that notion precise and give you an answer, which if the semi-classical approximation is good, should agree, this might be the hope, with the area in suitable units. So that's a proposal, that's just a, if you like, idea. It remains to be tested, and the really important thing here is there's been so much progress in understanding the matrix model I talked about numerically, really work by Hanada and his collaborators. Beautiful work which shows that the thermodynamics agrees and so on. So maybe a proposal like this, much harder to test than thermodynamics, maybe a proposal like this can actually be tested, and I think that would be very interesting. Even if it's not correct, I think we might learn something about how to make sense of bulk entanglement using these kinds of ideas from matrix theory. Okay, I'm about to end, but I have to say one thing just to clarify the difference between what I just was talking about in matrix theory and the very, very famous work of Tadashi and Shinzei Ryu, the Ryu Takenagi formula, which of course we've all heard about and is driving so much of the progress. You know, if you're talking about higher dimensional versions like the 3+1 dimensional version I was discussing of ADS-CFT, then the field theory itself, as we were discussing, extends along spatial directions. And you can ask how entangled are the degrees of freedom along these spatial directions where the field theory lives, how entangled is some of that spatial region with the rest, or some degrees in those spatial regions with the rest. And this is the question for which they provided a beautiful answer. So here it's shown, say we are in 2 spatial directions, yellow is B is the region of interest, and the answer they gave is that you compute the minimal surface in the bulk, which ends on the boundary of the region B of interest, and this area, this minimal surface in G Newton units is the entanglement entropy. It was a beautiful result. They conjectured it. We now know it is true, and it's driven much of the progress, as you all know. This is what I would call base space entanglement. This is entanglement along the directions in which the boundary theory, the field theory lives. What we are trying to do in what I was mentioning was understand the entanglement which is present along directions, which are present in the bulk, but not directions in which the boundary theory directly lives, but for which the boundary theory encodes the information in terms of various fields and degrees of freedom it possesses in the matrix theory in the form of matrices that are degrees of freedom in the system. So that's the difference. That's why I was calling it target space entanglement as opposed to this notion of entanglement, which we can then call base space entanglement. Okay, so that's the difference. Let me then summarize. Sorry to go a little over time. Entanglement is a key to understanding the strangeness of quantum mechanics, and increasingly people feel unlocking its full potential not only for physics but various branches of science and also quantum techniques and technology. We discussed how to define and make precise the meaning of entanglement in gauge theories, which are quite ubiquitous in nature, and also for matrix theories of the kind which are promising in our attempts to understand space and time in a fundamental way. I think much excitement lies ahead, so I think we look forward to the coming unfurling of these developments. And with that, let me stop and acknowledge my funding, and I'm ready to take any questions you have. Thank you very much.
Thank you very much for a beautiful colloquium talk. So just
Thank you.
So now it's time for the question. So if anybody have a question, just raise your hand and I just, okay. So Nakata-san, you do first, please.
No, I was just clapping hands. So thank you very much for the great talk.
Thank you.
So we do it. Okay, as I see by the list. So Takato, you do first.
Okay, I have a question about your definition, version 1 and version 2. So,
Okay.
what's the difference? I mean, if you calculate this entanglement entropy for some matrix model, do they behave in the same way? I mean, the scaling, like behavior.
Yeah, one can argue in general, I didn't have time to say this, but both should scale like n square at least, because the degrees of freedom you are tracing over, I'm just trying, basically a generic sector, because you have n total eigenvalues, generically you will have about half of them in the region of interest, and when you, in either version, basically you have a total of n square degrees of freedom and you're taking some fraction, order n square of them, asking how entangled they are with the rest. So the answer should scale with n square in general, but more than that, I'm not able to say in terms of differences. People have started computing some of this, but I think we are still at an early stage in terms of getting a full understanding of how either of these versions will behave for interesting gauge theories.
Is there any interpretation for the difference between version 2 and version 1? I mean, the version 2 minus version 1.
Yeah, that's a good question. That's a good question. I can't give you a very precise answer, but intuitively, you might think that the difference will be the entropy due to the strings cutting across, open strings cutting across the two regions. And so it should teach us something. If you compute version 1 and you compute 2, then the difference, as you're saying, should teach us about this extra entanglement. That's what one would hope. But I think we need to understand a little better, but that would be the kind of intuitive picture.
Okay, thank you.
Okay, thank you.
So, Haru Tasaki-san?
Yeah, thank you. It was a beautiful talk. I enjoyed. And as a low energy physicist, let me ask a question about the second part.
Yeah.
So you finally mentioned this decomposition of entanglement into distillable part and non-distillable part. That's very interesting. So what is the situation? Do you have like a general expression for this decomposition, or do you have to work out for each model, or what is the situation?
No, actually there is. Thank you for asking. I have some backup slides. I just try to go. Right. So we do have a general understanding, and roughly speaking, what happens is, because the flux has to meet this continuity condition across the region of interest, you can decompose the full Hilbert space into, as I was saying, a sum over tensor product Hilbert spaces. Each sector there is some probability you associate with various fluxes leaving the region of interest. That flux leaving the net flux leaving the region of interest, you cannot change by just doing manipulations, unitaries in the region of interest,
Right.
because it is fixed by the outside region. So the probability to be in any such sector it is specified by the net flux leaving at each point in the boundary, that probability is fixed and unchanged by unitary transformations. Therefore, it cannot be distilled. So the full answer has the following structure. There is a Shannon-like term, pi log pi, corresponding to these probabilities.
That's a
And
classical part here.
that's a classical part.
Yes.
And then there is a part which is the quantum part, which is the von Neumann entropy for each sector. So rho I is the density matrix in each sector, weighted by the I should have made this probability outside the trace, pi, sorry. So it's trace rho log rho in each sector, weighted by the probability to be in that sector,
Yeah.
And that's
Okay.
the distillable part, actually.
Very clear. Yeah.
Yeah, and now, so this is the general structure. In the non-abelian case, it turns out there's an extra term, and this extra term is roughly the following: that if you had at each point on the boundary a non-abelian flux coming out, you need to specify it in a gauge invariant way, and roughly what you have to do is create a singlet. So suppose the flux were transforming in the adjoint representation, you would have to create a singlet, because roughly the flux going the other way from the outside and one way from the inside produce a singlet. And so there's a kind of additional contribution due to producing singlets out of adjoints and so on, and that's the additional contribution here. But again, that's really a probability you can't change, and it's therefore a non-distillable part. So there's one additional term in the non-abelian case, but basically you have a Shannon-like non-distillable part consisting of then the first and third, and then a distillable part which comes out from each sector, weighted by the sector.
Yeah. Very clear. Thank you very much.
You're most welcome. Thank you.
Okay, so Saganagi-kun.
Sandip, thank you very much. Really wonderful talk. I have a question about your final point. So, do you have in mind some gravity dual is kind of cross section of sphere direction? Do you want to relate it to this target space entanglement?
Exactly, Tadashi. So, for example, if we took a sphere and we placed the appropriate constraint there, right, taking the half hemisphere, in principle, we can make that into a constraint. Now, there actually it turns out a little bit more complicated, because the natural objects, as you know, are the, say in ADS 5 cross S5 is the radial direction along with the 5 angles, because these are the x's. So if you just put it in terms of the angles, it is some pretty complicated constraint. And if you translate that into matrices, then because the matrices are non-abelian, you have to worry about factor ordering, when you translate it into matrices,
So actually, so you have actually 4 different definitions, because first of all, you can have a choice of subsystem. There part 1 and part, I think you have 2 possibilities of choice of subsystem, and another one is you can also put constraint for value of field. Right? You write it x1 is greater than a, or actually, long ago also we considered something similar problem for ADS 5 cross S5, and wanted to understand a cross section of S5, and we roughly claim that it's kind of block diagonal entanglement, but we didn't know precise definition at that time. And you have now 4, in my understanding, is that true? 4 different definitions? gauge
So,
invariant definition.
why do you say 4, Tadashi? At least for some simple constraint, like say, x1 greater than 0.
Yes, it is.
I was thinking of two definitions, depending on whether you keep these off-diagonal elements or not. But
what I had in mind, just without imposing any value of x, without specifying any value of expectation value, we can just, take a matrix and decompose into some small block and other blocks. And we can just trace out the other part, and you can define some density matrix.
Density matrix, yeah. The trouble we were having was without any constraint, we could not come up in general with a gauge invariant way to think of those blocks,
Yeah.
So therefore, once you have a constraint, then you can come up with a gauge invariant way.
I see.
Yeah.
Sorry, I missed that. I see. So in the end, you have two different definitions.
Two different, yeah.
I see. Do you know how these two behave different way? This entropy behaves different or something similar?
Yeah, so that's what was being asked also. Yeah, we haven't. It's actually not easy to do the calculations for any interesting system. So we are just starting to do them. We know that the general scaling is n square, but there should be interesting differences between them, and we haven't been able to calculate enough, so I can give you a good answer to that. I'm sorry.
Thank you very much. And now it becomes clear. Thank you very much.
Probably somewhat related to Takayanagi-san's question. If there is natural distribution, well separated distribution of these elements, in some sense there is a super selection. You can choose a super selection sector, but without having a concrete distribution of the elements, you don't really know how to choose a super selection sector. I think that's my understanding.
Yeah, that is right. That is right. If, for example, you were on the Coulomb branch, or you had the distribution of eigenvalues, then you can easily choose, some sector, as you say, in a gauge invariant way, right? Corresponding to those eigenvalues, right? Hello?
Yes.
Oh.
Yes.
Okay.
Yeah,
That's right. That's right, Masanori. So anyway, thank you for being here also. So anyway, because of Masanori's beautiful work, we hope numerically it may not be too hard to test some of this, but okay. Yeah, it remains to be seen.
Other question as well? If I am allowed to ask question, can I ask some question?
Of course. Go ahead, sir, please.
This is already related to somebody. So, but version 1, version 2, all relate to the off-diagonal element, whether you included it or not, right? That's my understanding. Am I right? If they are far away, obviously this off-diagonal element doesn't contribute much. But if they are close to each other, then we don't have a sharp meaning of the local position generically. Is that right?
Yeah.
Do you think this is so much meaningful to define whether you have a position X greater than 0 or not, even if they are close to each other, and then this off-diagonal element is so important, even in such a case?
Yeah.
If they are far away, I completely agree, off-diagonal element are damped by the mass, by the distance. So we do expect version 1 and version 2 of your definition doesn't change so much. But if they are tiny, local position in the bulk get lost. Am I right?
Yeah.
Then do you think it's so much meaningful to define, whether you included or not? I'm a bit not cool. I'm just asking. Yes.
I don't know. I don't know. In the strongly coupled matrix theory, that might correspond to this smooth gravity dual. Roughly, the question is how much entanglement is there right across the boundary?
Right.
And in any theory which is not UV complete, of course, you get a UV divergent answer in the bulk for this question. But we know that it's a beautiful fact if you wrote down area over for G Newton, and you took G Newton to be a renormalized value, right? That answer is finite, and Newton's constant gets renormalized in the same way as the ultraviolet cutoff which appears, in the entanglement entropy. So so it could be that what matrix theory is doing is giving us a nice regulator, because the answer will be finite in matrix theory. And maybe that answer does agree. It's quite a hope, but anyway, it agrees with area over 4G Newton. And then we can ask this bulk answer, which is finite, how much of that entanglement is across the cut, and that would come from these open strings going across. So I don't know, maybe those will provide a small amount in the end, when you take into account all the cutoff effects and so on. But before doing anything, it's not clear to me, at least.
If you include the off diagonal, then it is more or less guaranteed to obtain n square dependence. Am I right?
Then at least the counting will be n square. But what happens is, even if you don't include it, because you have to sum over all the sectors, at least for
okay, got it.
Yeah, then you still have a n square.
May I give one comment? So
yeah, please.
Yeah, after even strong coupling theory. So whether off-diagonal entries should be included or not, that ambiguity still remains. But actually, even when eigenvalue become very close, really almost across the string scale, you can actually make sense of location. So location actually makes sense. And there is a famous work by Portinsky in 1998, which says that in a matrix model.
Can you hear me?
Yeah.
How does that make sense? Even if they are so close and then off diagonal is dynamically excited? How?
So it will become a long story. So I can send you my paper later. But there is a famous argument against that idea by Portinsky in 1998, but there is a crucial mistake. Yeah, and I have a paper correcting the mistake. So, and I think slightly modifying this target space entanglement, it can actually make sense. I think I think this kind of approach can make sense even at shorter scale than Sandip is thinking, I think.
Okay. Yeah, I mean, okay, we have had a few exchanges. I also don't fully understand the point, but I see what Masanori is saying. But okay, yeah, maybe, yeah. I think the definition should work in general, just in matrix theory. And then we can see in various situations how much what contributes and what the bulk interpretation is. That also we can see. Yeah, at least roughly it should correspond to the entanglement across some region. One would hope. Yeah.
Okay, so any other question? No? Okay, then let's thank to the Sandip for the beautiful colloquium talk. Thank you very much.
Thank you very much.